Okay, so in today's lecture, we are actually going to tackle a very important theoretical question, and it relates to the universality of quantum computing. Particularly, we will see that how we can implement a general unitary transformation on any number of qubits using only the unitary transformations that act, two of the computational states. And in the second step, we will show that those unitary operations that act only on two computational states, they can be implemented using a single qubit unitary and controlled operations. So combining both of these things, we will be able to show that we can implement any general unitary transformation on any number of qubits using only CNOT gates and single qubit general unitary transformation. And as you know that we have already discussed that a single qubit unitary transformation can be implemented using up to a global phase using only rotations around two axes, let's say X and Y. So in the next lecture, we will see that how we can implement that general single qubit unitary transformation using only a discrete set of gates instead of a continuous set of gates that implements any arbitrary rotation. We will see that we can implement that single qubit unitary transformation using only a discrete set to any desired level of accuracy. And we will work out the gate complexity as well. Okay, what's the order of number of gates that we need to implement a general unitary transformation. Okay, so let me start sharing screen and recap this thing again. So our goal is, at the end of the day, at the end of the next lecture is to work out the a finite set of universal quantum gates of single qubit and two qubit inputs that we can use to implement any arbitrary unitary transformation on any number of qubits. And our path to this goal is going to involve three parts. Number one, we will show that any arbitrary unitary transformation on, let's say, it's some d by d level matrix where d is equal to 2 power n, where n is the number of qubits. Let's say we have 0, 1 all the way to n minus 1 qubits. And so it means the number of computational basis states that are available is equal to d, which is 2 power n. So any general unitary transformation that is composed of different types of gates, any combination you can think of, can be represented by ultimately a d by d matrix, okay, that transforms the inputs to the output. So let's say we can write it something like this. So this is a general d by d unitary transformation, which represents any quantum algorithm. So in the first step, we are going to show that we can implement it as a series of operations. For now, let me put m, because we will find out how many we need, such that each of these matrix is of this type. For example, this U1 is something like we have ones everywhere except at 4 places and zeros everywhere, except we have, uh, 4 places where we have non-zero element here and non-unitary element here. For example,
Sure.
Just a minute of now, let me give it structure. Let me give a particular example right here. Suppose I have some A here, B here, and some C here and some D here, something like this. So now we can see that this matrix, has 1 and zeros everywhere else. So it means any computational basis state that doesn't involve entries that corresponds to, these elements is simply multiplied by identity. But any basis state like this, 0, 1, 1. So if there's, 1, 1 here, this gets, multiplied with this thing. And these 2 elements also corresponds to, these 2 states. So only a state which has a 1 here or a 1 here is, impacted by this unitary. This is called a 2-level unitary transformation. So to be more precise, like this unitary transformation acts non-trivially only on this state and this state. Every other state is acted on by an identity matrix, because it's not impacted by anything, because only non-zero elements are present here and here that impact this computational basis state and this computational basis state. This is called a 2-level unitary operator. Okay, so in the first step, I'm going to show that any general unitary can be broken down into a product of 2-level unitaries. Go ahead, Afnan, what's your question?
वैसे ये पूछना था, मैं कंफ्यूज हो रहा था कि हम एग्जैक्टली कर क्या रहे हैं, लेकिन समझ आ गई.
Okay, so this is going to be the first step, that any general unitary which has, non-zero elements everywhere can be broken down into a product of unitaries which are 2-level unitaries. And I'm emphasizing that these are not single qubit operation, or these are not 2 qubit operation. Now we are using different term. It's called 2-level because it impacts only 2 computational basis states. So in the first step, that's what we are going to do. In the second step, we will show that how we can implement any 2-level unitary using only C0 and single qubit unitaries. So after this step, we would have shown that any general n qubit unitary operation can be represented as a 2 qubit CX and a single qubit Q. And if you remember, we have already shown that this single qubit U, can be written as using a combination of rotations. I think we showed for XZ, but actually in reality, it can be shown that any, 2 different directions can be used to represent these unitary. Yes.
सर जो हमारा फर्स्ट स्टेप है उसके अंदर अगर हमारी जो स्टेट है जिस पे हम एक्ट कर रहे हैं, अगर वो पहला 1 है और बाकी सारे जीरोस हैं, थोड़ा सुपर स्क्रॉल करेंगे इसको.
जी
सर अगर हमारा यहाँ पे जो हमारी स्टेट है ऑन द राइट, अगर इसमें हमारे पहला जो है एलिमेंट वो 1 हो और बाकी सारे जीरोस हो, तो उस स्टेट पे भी इफेक्ट नहीं होगा हमारे इस मैट्रिक्स की वजह से, क्योंकि जब हम
नहीं,
उसके
कुछ भी नहीं होगा।
सेकंड रो, अगर
नो नो
सेकंड
नो।
रो लेके मल्टीप्लाई करेंगे तो सी मान से मल्टीप्लाई होगा नहीं फर्स्ट एलिमेंट से।
Okay, so yeah, I haven't actually placed these C, D correctly. You're right. So these, they should be coming at C and D here.
ठीक है।
You're right. Thank you. So we have, we can structure it in a way that only these two states are impacted.
हमसे, लेकिन अब तो आइडेंटिटी की एक इंडेक्स की जगह सी आ चुका है।
तो कोई बात नहीं, वो इम्पैक्ट उसी वक्त होगा when you have a 1 here.
सही।
Okay,
ठीक है,
there's a 1 for everything else.
सही है सर, समझ।
Okay, thank you. All right, so in the second step, we will be able to show that we can implement using single qubit U and 2 qubit CX. Then in the third step, we will show, and no, in this single qubit U, we already know that using some, values of angles for these rotation matrices, we can represent this U. But these rotation angles were arbitrary. Okay, that it essentially means that we have an infinite number of gates. One gate, let's say, that rotates by 1 degree, the other gate that rotates by 2 degrees, the other gate that rotates by 3 degrees, and so on. So to implement arbitrary single qubit unitary, we essentially need, if we want to implement it exactly, an infinite number of these gates. But
हमसे
in the third step, we will show, just a moment, please, that these arbitrary single qubit unitaries can be simulated by a discrete, and fixed set of gates. Particularly, we will actually show that only Hadamard pi by 8 and actually we will be able to show that only with Hadamard and pi by 8 gate we can approximate these unitaries to any desired Persian epsilon using only these two gates. And then with this and CX, we will be able to show that we can implement any unitary up to the desired Persian. So this is going to be our roadmap. Go ahead, Afnan.
हमसे वो मैं यू वाली लाइन से कंफ्यूज हूँ कि आर एन और आर एम क्या चीज रिप्रेजेंट कर रहे हैं, ये ब्लॉक्स
These are the directions of axis. Last time we were discussing, I think one of them was x-axis, the other one was y or z. I don't remember. I can check actually. So if we have access to rotations around two different axes, we can actually implement any. This was z and y. So we had shown that if this is z and this is y, this is z, we can implement any arbitrary u. But the result is even more general. They don't even have to be orthogonal axes. Any two different axes, let's say this is some m axis, this is some n axis, and if we have access to gates that can implement rotations around these two axes, we can implement any arbitrary unitary.
Okay, sir.
All right, so let's begin with the first part. Okay, and they're actually in individual component wise, they're not very complicated, and hopefully by keeping the overall picture in mind, you can appreciate. And the goal actually in this lecture is not to give you a way to later implement any quantum algorithm using these steps, because we will see that this is really a very inefficient way, because we are going to be needing exponentially many gates, but only to prove that any arbitrary quantum algorithm can indeed be implemented using single qubit discrete set of gates and a control X gate. But of course, it's the scientists who work on quantum algorithms, the job is always to come up with an efficient quantum circuit that implements with fewer and fewer quantum gates. So this is not per se a method, to give you efficient quantum algorithm, but only to prove in principle that we can implement any quantum circuit. And
हमने लास्ट क्लास में किया नहीं था ये, हमने एक
नहीं, उसमें
arbitrary
तो हमने
unitary
बड़ी
operator
रिस्ट्रिक्टेड एक दो चीज की थी. We didn't show that any unitary can be implemented. We just discussed, I think if I remember correctly, at the end we were discussing any like C and U can be implemented using that particular scheme. But all unitaries, sorry, C and X, I think also C and U. So any, n bit controlled unitary. But, a general unitary can be much more complex than this simple thing.
Okay, sir.
Okay. Okay, so let's begin with the first task. And that is the two-level unitary. As you know, universal construction for quantum gates, and then we will show the breakdown of two-level unitaries. And for this, let me begin with actually a simple matrix and show you how we can, write it in terms of two-level unitaries, and then you will actually be able to appreciate the general method that we can use to apply to any dimension. So let's begin with a 3x3 matrix. And just to, FGHE, to clarify that usually when we have unitaries, actually we can never have a 3x3 unitary, because the unitary that we will have, they will always be like 2 power n. So either 2x2 or 4x4 or 8x8 and so on. But for the for simplicity, I'm taking this 3x3 because this can then be used to show how to reduce the matrix into two-level matrices. Anyway, so let's work with this one, and our goal is to show that we can write this. We can find three matrices: U1, U2, U3, where U1, U2, U3 are two-level unitaries, such that this product gives us identity. Because once we have this, then I can write it by applying the inverse of U3 on both sides, and then inverse of U2, and then inverse of U1. We can show that this U is like this. And since this is two levels, so these complex conjugates are also two levels. So this will then show that this arbitrary unitary has been written as a product of these three two-level unitaries. Okay, so for this, let me first quickly review. If we have a two-level unitary, what it means to be this unitary matrix. Its complex conjugate is A conjugate, and here I will have C conjugate, B conjugate, and D conjugate. And for this to be unitary means that U dagger and U dagger U, they should both be identity. So U dagger would be AQ, and this, and then AC star plus BD star, and similarly C A star plus DB star, and then C mod square plus D mod square. Similarly, you can work with this. So for this to be identity, this has to be 1, this has to be 0, this has to be 0, and this has to be 1. It means that a unitary matrix has elements, that satisfy these relations, that A mod square plus B mod square. So this is A and B. So all the elements in each row, their absolute value square should be 1. So this mod square plus this mod square should be 1. Similarly, this mod square plus this mod square because of this should be 1. And then the product of C with A conjugate plus the product of D with B conjugate, their sum should be 0. And similarly, you can check for cross elements from the second one as well. Okay, so this is the properties of unitary matrices. And let me now get back to this one. So this is the U that we have to work with: A, B, C, D, E, F, G, H, E. Okay, now the trick is that I first want to have a number 0 at this place, because we saw that two-level unitaries have a lot of zeros on off diagonal entries. So let's start from this. So let's try to make this be 0. So we need to find out some matrix U1, which is a two-level unitary. But when I multiply this U1 with U, I need to get this B0. So I'm assuming that B is not 0 to begin with, because if B is already 0, then I can take U1 to be just an identity. But assuming B is not 0, then I can write this U1 like this. I want 0 here. So whatever this matrix is, its second row should have a special construction, because when second row will get multiplied with the first column, I will get this element. So to get 0 here, my second row can be like this, that I can have B here and something like minus A here and 0 here, because now when I multiply this row with this thing, you can see that this will be B into A minus in, yes.
वो this वाला समझ नहीं आ रहा कि क्या, मैं नजर नहीं आ रहा कि this कौन सी row.
Oh, okay. So I am trying to find a U1 such that if I multiply this U1 with U, that and I have this U1 into U, I need to get a matrix that could have anything anywhere but a 0 at this place, at the second entry place in this first column. So to get this 0, I need to have a second row which has a structure like this. Now my first row can be like this, because I need to make sure that this is a unitary. So it means that first of all, I have to normalize it, because each row is normalized. So this has to be divided by B square plus A mod square square root, and this has to be divided by B mod square plus A mod square. And this I'm doing simply to normalize this row, because I know that each row in the unitary matrix is normalized to begin with. Now, since I have like this here, then I was discussing these relations for a unitary matrix. To satisfy these, the first row can be automatically given to have these elements. I should have its conjugate here. This is a real number. And then B conjugate, B square A mod square. And then 0 here, 0 here, 0 here, and 1. Now you can check a few things for this one. So I started from this, that I wanted to make this B0, an element at the place of B0. And for this, I figured out that this second row in this unitary has to have this form, that since this is going to be multiplied with the first column, element B here, and so that when this multiplies with A, I get AB, and minus A here, so that when this multiplies with B, I get minus AB, and the sum is 0. The third element is made 0. And also I know that in each unitary, each row is normalized. So I divided with the A square plus B mod square square root. Now, once I have these two elements, the first two elements can easily be found from the properties of unitary matrices. And to make sure that its dagger is its own inverse, its inverse. So this unitary U1 is a two-level unitary, which when I will apply it to U will give me something like this. So there should be, some, let's check what I get at this place. So A, D, G gets multiplied with A star, sorry, U1 is coming first. So A star, B star 0 gets multiplied with A, B, and C. So A star into A plus B star into B will give us A mod square plus B mod square. And we have this, the square root at the bottom. So I essentially get some number, let me call it just A prime. Okay. And there will be 0 here. And there is some number, let me call it C prime. And then I will have some number here, A, B, C, D, E, F, G. So let's call it actually I. Okay, so everyone is okay with this one? U1, U?
sir, पहले वाला 1 over A square plus B square whole under root नहीं होगा? वो तो हमें पता नहीं है.
कुछ भी, let's just call it A prime.
Okay.
Instead of writing all of it.
सर वो U1 के अंदर हमने पहली रो के अंदर वो A स्टार और B स्टार वाली टर्म्स क्यों डाली हैं? बिकॉज आप कह रहे थे खाली हमें B वाली लोकेशन के ऊपर 0 करना, बाकी हर जगह जो मर्जी हो हमें फर्क नहीं पड़ता.
जी, गुड क्वेश्चन. सो उसकी वजह ये है, I also want to keep this U1 a unitary matrix. So to keep it a unitary matrix, I have to make sure that entries here are such that it's, when I take its dagger, it becomes its own inverse. So for that, there has to be an element, first of all, that whose row is normalized. So this has a normalized row because A mod square plus B mod square square root will be cancelled by A mod square plus B mod square. Okay. And the second thing is that these product terms had to give me 0. I had to arrange them in such a way that A into C star plus B into D star gives me 0. And there's a negative sign here, so I didn't put a negative sign. Now you can see that A star into B plus B star into minus A will give us a 0. So to make sure that this is a unitary, we have to have these two elements here. Okay, Subhan?
Yes, sir.
Perfect. So this is, the main point, because once we are able to see how to get this, the rest is, going to keep following with the similar tricks. Now, the next step is to, come up with some matrix U. Let me call it U2, which is a two-level unitary. But when I multiply it with it, I get a 0 at this, at the location of C prime. So for that, we can see that U2 should be of this type. Some A prime star there's a C prime square. We put a 0 here. Let me first write it and then we can discuss it. One, 0, 0, and So this is just U2. Now you see, I wanted to get a 0 here at the location of C prime, which means that my last row should be such that when I multiply it with the first column A prime 0 C prime, I should get a 0. So first of all, I can put a 0 here, because even though I could have put anything at this location of 0, but I want to, you know, have as many zeros and ones, because at the end I also want to keep it a 2-level unitary. So let's put a 0 here, and there's an A prime here and a C prime here. So it means that I can just interchange the location and put a minus sign with one of them. So I interchange the location. So this is C prime, this is A prime, sign is changed, and then I normalized it. And once I have these two elements, I can easily, figure out the other elements. So these two elements, the top row is also written, which is still normalized, and you know this is still a unitary matrix. But now when I multiply it with U1 U, let's see what I get. I get U2 U1. So this A prime star into C prime star, this will give us A prime mod square, C prime mod square, and divided by A prime mod square plus C prime. So we'll get, you know, something, let me call it just A double prime, D double prime, 0 here, something here, and this was some G prime. Actually, we can even do better, because I want to get a 1 here. So instead of just, you know, because I got A prime mod square plus C prime mod square over here. So what we can do that we can, okay, let's keep going. G prime and H prime and J. Actually, I could have gotten 1 here as well with the same matrix if I, instead of using this square root, if we just use these numbers without square root, will it still be a unitary matrix? Let's see. If I don't have a square root here, then when we multiply it here, I would get A mod square plus C mod square, and this would be cancelled with A mod square plus C mod square. We'll get a 1 here, and will it be normalized? A mod square plus C mod square. Yes, it would still be normalized. No, it will not be normal. Okay, so we can keep it like this, but then in the next step, what we can do is we can have a matrix like this. It's not even a 2-level matrix, it's like just a matrix like this. So when we multiply this matrix with this one, all we will do is make this 1, and we will get a matrix
Is
like
this unitary?
this one. Let's check. If
इनसे
I,
हमारे तो U1 U2 इस तरह उनके अकाउंट बढ़ नहीं जाएगी जितनी हमें चाहिए थी. अगर हम इस तरह मतलब अपनी मर्जी से
Well,
वाली करने के लिए
we can have
बिल्कुल नया
more
matrix-
unitary matrix for now. So let's say if it is a unitary or not. If I, is it, it's conjugate in complex conjugate. Well, it's not a unitary matrix actually. This 1 over a double prime, yes, this is not going to be unitary, because if this is not 1, this first row will not be normalized. And you know, one thing that we require for unitary matrices that their rows are normalized. So let me,
सर हम कोई और एलिमेंट डाल के उसको नॉर्मलाइज कर नहीं सकते थे, सर यूनिटरी बना नहीं सकते थे?
let's see. So actually, what we can do is introduce the idea of global phase, because if I take a double prime common from this thing, then I can make it 1 up to a global phase. So let's do that. So let me take this thing common. So there's this 1, and then there are these elements which are divided by a, but then now I have some global phase element over here. So if we can show the product up to global phase, then we should be okay. Okay, so we now have 1 here, which means that if we can have 1 here,
सिर्फ वो कॉमन लेके ग्लोबल फेस कहाँ पे आएगा, वो आप पॉइंट कर रहे थे, वो फिर पता नहीं चल रहा था.
so this would be coming here, somewhere here.
Oh, okay.
Okay, so once we have 1 here, it means that these d prime and g prime, they have to be 0 for this to remain unitary, because they have to be normalized. So if this is 1, it means that this is already in this form. I will actually check this point again if there is a way to make this, even this
sir,
part go away. Yes.
हम ये कर सकते हैं कि हम U1 के साथ E नेगेटिव आयोटा अल्फा लगा दें, वो तो हमारी मर्जी है ना, तो अब जब ये दोनों मल्टीप्लाई होंगे तो ग्लोबल फेज भी गायब हो जाएगा.
Yeah, we can do that. Yeah, you're right. So the point is that once we have 1 here, then it means that these 2 elements have to be 0 because of the normalization of each row. And since we have been multiplying with unitary matrices, so our result is also unitary. So it means that as soon as we get 1 here and zeros here, these 2 elements are automatically 0. We didn't work them out, but if we had worked them out, they would be coming out as 0. Okay, so once we have this,
हमसे ये जरा पॉइंट दोबारा से रिपीट कर देंगे कि जो ऊपर वाले हमारे डी डबल प्राइम और जी डबल प्राइम ये 0 हमने किस तरह से किए हैं?
क्योंकि हमारा जो हर यूनिटरी मैट्रिक्स है ना, उसकी ये प्रॉपर्टी है कि जो ये एलिमेंट्स है ना रो के, दे हैव टू बी देयर एब्सोल्यूट mod square should add to 1. A mod square plus B mod square plus जो भी रो के एलिमेंट्स है, they should all come to 1 to make sure that U dagger is identity.
ठीक है, और हमने जो फर्स्ट एलिमेंट है उसको 1 हमने इस तरह किया है कि उसमें से जो फेस था वो हमने कॉमन निकाल लिया.
जी, because that's a term that we can take common, so we can just put it there. And also
तो सर हाउ आर वी
Afnan
श्योर
pointed
कि
out
वो
that we
सिर्फ
can,
एक फेस ही होगा जो फर्स्ट टर्म है हमारी, जो ए डबल प्राइम था?
That's a good point, because it could be, a number
any भी हो
with a
सकता है.
magnitude that is not 1.
Yes.
So let's actually go back if we can see it again. So if I have u1 like this, then this number was coming out to be a prime mod square plus b prime mod square. So this was like this, divided by, so this is actually nothing but this square root, right? And this number would be a into c prime So let me check this point out. I will work out each product differently, and then we'll see how to deal with that. But for now, let's imagine that we have been able to get 1 over here, and once we have 1 here, these elements should go to 0 because of the normalization of each row, and then we are left with only a 2-level entry here, and we can construct another unitary U3 just like this, 1 0 0 0 0, and we can just put its inverse over here. Okay, so and actually we don't even need to do that. We can find its inverse very quickly, because these u1 u2, they're all unitaries. So it means that this is a unitary, and for this to be unitary, this part already is a unitary matrix. So all we need to do is put its dagger over here, and this would automatically become its inverse, and which means that now u3 u2 u1 u, this will give an identity matrix. And from here we can see that u is u1 dagger, u2 dagger, u3 dagger.
sir?
So
तो हमारे पास फिर कोई भी किसी भी लेवल का सिस्टम हो, हम बस पहले कॉलम और पहली रो को 0 0 कर दें और पहले में 1 रहने दें, और जो बाकी सारा बच जाए उसका इन्वर्स ले लें u3 में.
But we can do it only if we start with 3 by 3. Now if we start with 4 by 4,
फिर भी यही कर देंगे ना.
so in 4 by 4 we will first convert using 3 unitary u1 u2 u3, and this will come to 1 0 0 0 0 0 0, because as soon as we make these 3 elements 0 and this 1, then these 3 will become 0, and we will have something over here like a b c d e f,
और इसका इन्वर्स ले लेंगे
g h i.
u4 में.
No, we that actually have to be worked out, because this is not this is still unitary, but this is not a 2-level system. So we can find its inverse by using that dagger thing, but we are not only interested in finding inverses, we are interested in finding matrices that are 2 levels. So its inverse will not be a 2-level system.
Yes, हम वो 2-level चीज भूल गया था.
We will need another 3 matrices, 2 for these zeros and 1 for this, and
Yes,
ultimately
sir.
we will need u1 u2 u3 all the way to u6.
सही है.
So we will need 6 unitary matrices to break it down into 2-level unitaries.
सही है sir.
And similarly, if we have 5 level, so we will need first 4 unitaries to put zeros here, then we will need, you know,
सर वो हेयर नहीं
4,
समझ आता।
sorry,
जब हेयर कहते हैं ना तो हमें पता नहीं चलता आपका माउस किधर है।
यार ये थोड़ा सा इशू है, let me work it out. I'll find a way to, you know, show you the mouse as well. Let's see if in the Zoom there is some way of,
वो पॉइंटर होता है मेरे ख्याल से। जब
so,
स्क्रीन शेयरिंग चल रही होती है ना तो ऊपर एक बार आ रही होती है, तो उसके अंदर वो एनोटेशन होती है, ऐसा कुछ पता है मुझे याद नहीं है। तो वहाँ पे वो एक पॉइंटर की ऑप्शन होती है, एक लेजर होती है।
अच्छा, so let me see, हाँ, there's so it's a portion of screen, video, picture, audio, portion of,
आई थिंक वो तब आएगा जब स्क्रीन शेयर हो रही हो, चल रही होगी।
let me see now.
सर
अब
ये
ऊपर एक
वन
बार
नोट
आ
में
गई
ऑप्शन है।
होगी।
Can you see the mouse now?
सर माउस नजर आ रहा है, लेकिन जब आप राइट करते हैं कुछ या फिर जब आप होवर कर रहे होते हैं अपने पेन को उसके ऊपर, तो हमें वो नजर नहीं आता। उसके
अब
लिए
नहीं नजर
आपको
आ,
नहीं, अभी सर आपको ऊपर ना एक ग्रीन कलर की बार नजर आ रही होगी जूम की अपनी,
हाँ हाँ ठीक है,
उसकी ऑप्शन में देखिए, वहाँ पॉइंटर की ऑप्शन होगी।
let me see, ठीक है। यार यहाँ तो कहीं नहीं आ रही।
खैर ऐसे फिर आप अगली क्लास से पहले अगर आप देख लेना, अभी इतना वैसे जरूरी तो नहीं है।
सर वन नोट में अवेलेबल है ये ऑप्शन।
वन नोट में है?
जी सर। सर जहाँ पर पेन है ना, पेन बने हैं, सर वहाँ पर एक एरो बना होगा, तो वहाँ पर एक ऑप्शन होगा टू यूज पेन एज अ पॉइंटर।
चलो यार मैं इसको फिर देखता हूँ बाद में, सॉरी। एक तो तरीका ये है कि हम वो बोर्ड वाले लेक्चर्स पे शिफ्ट हो जाएं।
सर बोर्ड वाला बेहतर होगा,
हाँ
क्योंकि
उस पर
उसके ऊपर
फिर,
वो
लेकिन इस
पिक्चर
तरह
वाला
नोट्स मिल जाते हैं
एग्जाम
सर।
होता है।
हाँ इसका ये फायदा है कि नोट्स मिल जाते हैं ये। चल आई फिगर आउट आइदर द माउस, और या जो है वो हम बोर्ड पे शिफ्ट हो जाएंगे। अच्छा बहरहाल, तो अगर आपके पास 5x5 मैट्रिक्स है, तो फर्स्ट यू नीड 4 गेट्स टू हैव you know 4 zeros in the first column, and then you will need 6 more gates just like this. So essentially, and this, you know, and if you have 6, then you add 6 more and so on. So the number of gates are scaling something like proportional to d. The higher the dimensions, you know, more gates you need. It's not d square. For example, for 6 you don't need 36, but you need 16. So it's not scaling d square, but it's, you know, proportional to d. What's the dimension of your unitary matrix? Roughly you need the same order of gates to convert it into number of 2-level unitaries. Okay, so any comment?
फिर बाद में जब हम कंप्यूटर में काम कर रहे होंगे तो हम कोई भी मैट्रिक्स, जो भी मैट्रिक्स देना होगा दे देंगे और एक फंक्शन बना देंगे, वो तो हमें खुद ही उसके यूनिटरी वो बना के दे देगा ना उसी वक्त ही, रियल टाइम में।
अगर आप इसको इम्प्लीमेंट करना चाहते हैं तो it can easily be implemented.
अच्छा
because all these matrices are dependent on the elements of the starting matrix and then what you get after.
Yes, sir.
Okay, so let's now go to the second step, which is showing that single qubit and C naught are universal. That I can implement an arbitrary two-level unitary operation using quantum circuits that contain only single qubit gates and control X gates. And the trick for this is what is called grayscore. So let me actually do it with an example, because I think that will illustrate it the best. Let's say you have a two-level unitary matrix like this. Zeros all the way to B, ones all the way to second last, and then D.
टेस्ट मैट्रिक्स हम करना क्या चाह रहे हैं?
So this is a matrix. So this is, what the type of two-level unitary matrix that we broken down our general unitary matrix to, right?
Yes, sir.
This only have non-zero and non-unitary element over here, 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 and here. This is an 8x8 matrix. So let's see how we can implement it in circuit. अब इसको अगर आप देखें तो ये सिर्फ जो एक स्टेट है 0-0 और जो 1-1-1 स्टेट है, इन पे नॉन ट्रिवियली एक्ट करता है, एक्ट नॉन ट्रिवियली only on these two states. Remember, this is an 8x8 unitary, so this is a unitary transformation that acts on 3 qubits, because 3 qubits operations can be represented by matrices that are 8x8. So 2 power 3 times 2 power 3. So this computational state 0-0-0 is represented by 1-0-0-0 all the way this, and this 1-1-1 state is 0-0 all the way to 1. And every other state has a 1 somewhere in between. So it's a identity matrix if your one non-zero elements come at a location other than the first and the last place. So it acts non-trivially on these two states, 0-0-0 and 1-1. Is that clear?
Yes, sir.
Okay, so now the trick to implement this U is what is called grayscore, and it works like this. So suppose you have this 0-0-0. So you write it like this. Let me write, this is some qubit A, qubit B, qubit C. And then you go from this to this by changing only one qubit state. So let's say one way of doing is that I make it 0-0-1, then I make it 0-1-0, and then I make it, 0-1-1, and then I make it 1-1-1. Now you see, I started from here and I reached the others. You can start from this and go to the other one. It doesn't matter. And in each iteration, I only changed the state of one qubit. This 0 went to 1. These two are the same. And then this and this is the same, and this is changed. And then this and this is the same, and this is changed.
So ये नहीं समझ आई क्या हो रहा है?
ये एक method है. It's called the grayscore method to implement this U. And
जब हम करेंगे ना?
हाँ, first you understand is how it works, and then we'll see why it works. So we have two computational. For a two-level unitary, we will always have only two computational basis state that the matrix act non-trivially. And then we begin from one state and we go work out the other state by changing only one entry of the qubit, one of the qubit. ठीक है ना? And then let's work out the circuit. So suppose this is qubit A, qubit B, and qubit C. And we work it, the circuit is worked out like this. So this is the same state, 0, 0, and C is changing. So we implement a control NOT gate that is controlled by the qubits that are same, and the control is actually specified in this way, that if it is a 0, it's controlled by the control is like this. It's controlled by 0, 0, and then this bit is flipped. Now we have reached this point, and then from here to here we see that this and this qubit is same, and this is changing. So I'm implementing the control on this one, and this qubit is 0 in both cases. So this is a control like this, and the C is in one state. So this is a control with a dot. And after this, we don't do the last one. And then what we do is we implement our unitary, our smaller unitary transformation A. So we have A, B, C, and D. So A, B, C, and D. And this unitary, we act on the qubit which is different. And this is controlled by the other two qubits that are same. Like this. And then we reverse this part. So we have this dot and hole, and we implement the circuit again. And then we have these, a NOT gate controlled by these. And we claim that this circuit implements this unitary transformation using C NOT gates and this control unitary. Now I'm not explaining the breakdown further, because in the last lecture we showed how to implement this, Toffoli gates that are controlled by these two qubits, and you also know how we can implement using control NOT gate and using this arbitrary transformation. This control U tilde can also be implemented only using this U tilde and using C naught. So once we have done here, we just reverse it. So any question about this method? I haven't shown until now that it really works. I'm just showing how it works, and later I'll show how we can see that it actually implements the same matrix. Actually, let me take another example. And then I'll show how we can say that it really does what it does. 1, 0, 0. This is still a 3-qubit implementation, but we now have a unitary transformation like this. So now you see that this acts non-trivially on states that have a 1 here at the second place and the 1 in the last place. So this state and this state. And this is the computational basis state which I think is given by, so this is the one which is given by 1 1 1, and this is the one which is given by, if you want to work out, this I think is 0 1 1. No, sorry, it's 1 0 0. Let's just check. This 1 0 0 state is 1, tensor 0, tensor 0. 1 is 0 1, 0 is 1 0, 1 0. So this 0 1 into 1, this 0 into 1 0 will be 0 0. This 1 into 1 0 will be 1 0. Tensor, this 1 0 is as it is. Now this 0 into 1 0. So this is 0 0, 0 into 1 0 0 0. 1 into 1 0 is 1 0. Okay, so this is not it. So let's check out the 0 1 1. Actually, it's 0 0 0. Let's check out this one because this is the second. Let's check out this one. So this is 0 is 1 0, 0 1, 0 1. 1 0 1 0 0. I can see that if this would have been 1 0, for 0 1 it was 0 into 0 0, 1 into 0 1. So it's not even this. We had this 1 at which place? At the third place, 0 0 1. So let's work out this one. 0 1 0. This is 1 0 0 1 1 0. So 1 into 0 1, 0 into 0 1, 1 into 0. So 0 into 1 0 1. Yes, so this is the state. So it acts non-trivially on 0 1 0 and 1 1 1. Okay, so this matrix acts on 0 1 0 and 1 1 1. So for grayscore construction, let's begin from 0 1 0. So then I change this 0 1 1, suppose, and then 1 1 1. Now for, let's say, A, B, C. Now for this thing, we see that this one and this one is the same. So this is controlled by O, this is controlled by dot, and I implement an X here. We don't go to the last one, but you see that between these two, this is common. So B and C, and then A is different. So I implement U tilde here, and then I reverse it. Okay. So this is the circuit that I claim implements this unitary transformation. Okay, so everybody gets the method. Or is there any trouble how to implement the method?
सर बस एक दफा अगर आप फिर से रिकैप कर दें मेथड।
So हम दो वो states identify करते हैं जिन पे two level system non-trivially act करता है. So two
जी
level
सर।
unitary by definition acts non-trivially only on two computational basis states. And then we
Yes,
begin with one and construct a grays, what is called a grayscore, जिसमें हम एक वक्त में एक bit को change करते हैं and we go from this all the way to this.
पर हमने 111 तक जाना होता है।
हाँ, so
ठीक
जैसे
है।
इसमें हमने एक को change किया, फिर यहाँ पे इसको किया, so we reach this thing. And then we construct the circuit like this. So in the first two, we identify what is common. So this one and this qubit is, this and this qubit is common, A and B. So we have a control affected by A and B, and there's an X gate on C because C changes from 0 to 1. So there's an X gate here, and then we don't do the last one always, only up to the second last. And then we implement this U tilde on the qubit, which is different between the second last and last, controlled by the qubits which are same. So it's 1 1. So there's a control by 1 1 and by controlled by B and C qubit. And once we have implemented U tilde, we just reverse all the gates that we have implemented before.
सर जो सा लास्ट वाला होता है उसके ऊपर हम यूनिटरी ऑपरेटर लगाते हैं ना, जो आखिरी स्टेप में 1 आता है।
जी जी।
तो यहाँ पे तो आपने आखिरी स्टेप में वो कोई यूनिटरी ऑपरेटर लगाया ही नहीं हुआ।
नहीं, ये लगाया तो है, ये U tilde।
सर तो सेकंड स्टेप में नहीं आ गया।
नहीं, आखिरी स्टेप यहाँ पे हो गया। Then this is just the reversal of what was done here.
सही है, सही है, सही है।
So there are three parts to the algorithm. In the first part, क्योंकि यहाँ पे एक ही गेट है, ये थोड़ा सा जरा लेस है। यहाँ पे देखें, यहाँ पे थे एक गेट इधर था, एक गेट ये सेकंड थर्ड स्टेप में था. So we have these two gates, and then we had unitary for this part, and then this part just the reversal of what was implemented here. So this gate was lost, so this is first, then this was here, then this is, and then we reverse it.
हमसे तो सिर्फ कंफर्म करने के लिए मैं आपको बस ये बता रही हूँ कि मुझे भी ये समझ आ रही है कि जो हमारा मैट्रिक्स होता है उसे हम वो टू लेवल से, मतलब टू लेवल के लिए हम उसे ब्रेक डाउन कर लेते हैं और वो U1 U2 U3 हमारे पास आ जाते हैं उसी ऑर्डर के जिस डायमेंशन का हमारा मैट्रिक्स होता है। फिर हम उससे आइडेंटिफाई करते हैं कि नॉन ट्रिवियली कौन सी स्टेट्स पे एक्ट करेगा। वंस वी आइडेंटिफाइड दो स्टेट्स, उनके बाद वो स्टेट्स हम पकड़ते हैं और उन पे ये वाला मेथड रन कर देते हैं और इससे हमारा सर्किट बन जाता है। तो हम एग्जैक्टली यही कर रहे हैं ना?
बिल्कुल
सही है सर।
सर हमारा जो यूनिटरी है जो फर्स्ट क्यूबिट पे एक्ट कर रहा है, उसके बाद वो हमारी जो बिट है वो चेंज नहीं हो जाएगी। तो हमारे पास हम जब वही जो उसके रिवर्स ऑपरेशन लगा रहे हैं, क्या पता कि वो ना लगे अगली बार में।
हाँ, so the next step is to show really that it actually does what we are saying that it does. So let me begin from this one. Okay, the second example is a bit simpler. So this U acts non-trivially only on, you know, these states. So it means if we have a matrix U act on the state 0 1 0, we get U 0 0 1 0, and this actually gives us, if you really implement this this U on this one, we will have an entry here A plus C. This would be 0 0, A plus C 0 0 like this. And if you implement U on this 1 1 state, you actually get 0 0 0 0 B plus D at the end. And if you implement unitary on any of the other state, for example 1 1 0, you'll get the state 1 1 0 back. So this is what this unitary does. And let's see if this implementation really implements this unitary or not. To do that, let me start with, let's say, this state 0 1 0. So if this is 0 1 0, so this is 0 1 0. So over here, after this one, So this is 0, this is 1. So this will be changed. So this, because this is 0, this is 1, this control AB will be impacted and I will get 0, 1, 1. But once this is 0, 1, 1, this is 1, this is 1. So this control is affected and this U star will be impacted on 0. So I will get actually this U tilde on 0 and this 1 and 1 will be as it is. And let's see what this U tilde 0 is. U tilde 0 is A, B, C, D, and this 0 state is 1, 0, 1, tensor 1. So this is going to be A. So this is A into 1 into C plus B into 1 into 0. So I will get A, and I will be having B here, right? So this is A, and this B into D into 1, 0 will be, so I'm getting tensor 1, tensor 1. Okay. और ये जो A B है, this is nothing but A 0 B 1 tensor 1 tensor 1. So I actually get A 0 1 1 plus B 1 1. यहाँ तक आ गया. So let's see what happens to 0 1 1. So if it is 0 1 1, so this is 0, this is 1. So this is, changed to 1. This is changed to 0. So 0 1 1 goes to 0 1 0 into A, and this B remains as it is. So this is nothing but 0 0 A into B. And this was not what I wrote here. If the input is, let me check it again if I wrote it correctly or not. So let's say what happens if I implement this state 0 1 0, and this, when this multiplies with this matrix, what do we get? We get A here and B here, right? क्योंकि यहाँ पे 1 आ रहा है ना. So ये तो 0 है, so this CD will not come here. When this multiplies with this, I get A here and B here. ये मैंने सही नहीं लिखा था. So when A here and B here, and that's exactly what we get at the output here. ठीक है हैदर? बिलाल हैदर?
जी सर, यहाँ तक तो ठीक हो गया, लेकिन उसके बाद जब हम उसको रिवर्स करेंगे.
नहीं, हमने ये देखे रिवर्स करके ही, दिस इज जस्ट द आउटपुट. दिस इज द आउटपुट एट दिस पॉइंट.
सर लेकिन जो हमारी फर्स्ट क्यूबिट है, अब वो एक सुपरपोजिशन स्टेट नहीं है ए और बी वाली.
देखिए मैंने गेट्स को रिवर्स करने का कहा है कि उसी रिवर्स ऑर्डर में गेट लगाएं. इसका मतलब डेफिनेटली ये नहीं है कि स्टेट भी रिवर्स होंगी, बिकॉज वी हैव अ यू टिल्डे इन बिटवीन. तो आपने ये सही नोट किया था कि यू टिल्डा है तो जरूरी नहीं कि स्टेट, तो स्टेट तो रिवर्स नहीं हो रही. इसीलिए वी स्टार्टेड विद 0 1 0 बट वी एंडेड अप विद A times 0 1 0 plus B times 1 1 1.
ठीक है सर, आगे समझ सही.
Okay, so state is definitely not being reversed. It's just the construction, it's the gate construction that people have discovered, that if you implement in reverse order, then this circuit implements exactly the two-level unitary that we were talking about. Okay.
तो सर अगर एक साथ B की भी स्टेट आ रही है, एक सुपरपोजिशन स्टेट अगर आउटपुट में मिल रही है, तो the circuit is doing a little more than just implementing the gate,
नहीं वही कर रहा है जो करना चाहिए. देखें ये जो U है ये भी तो यही कर रहा है ना, कि you give it one state, it give you a superposition state of 0 1 0 and 1 1 1.
तो हम वैसे ये तो समझ आ गई है, लेकिन हम didn't we start from this idea कि हम करना ये चाह रहे हैं कि हम एक कंट्रोल्ड ऑपरेशन इम्प्लीमेंट करना चाह रहे हैं किसी एक क्यूबिट के ऊपर, तो फिर बाकियों को अनअफेक्टेड नहीं रहना चाहिए इन थियोरी?
नहीं, हम गेट्स पे सी नॉट लगाना, सिंगल सी नॉट यूज करना और बात है, और स्टेट्स तो हमें एबिलिटी तो चाहिए कि हम जनरल कोई भी यूनिटरी इंप्लीमेंट कर सकें जो सुपरपोजिशन भी क्रिएट करता हो, जो ना भी करता हो।
यस सर।
ठीक है। And what you can do actually that check that अगर आपकी सर्किट की इनपुट ये जो दो नॉन ट्रिवियल स्टेट्स थी जिन पे ये कर रहा था नॉन ट्रिवियल, उसके अलावा कुछ इनपुट देंगे तो यू विल गेट द सेम आउटपुट।
अच्छा सर, वन लास्ट थिंग, हम यानी कि आउटपुट एक्सपेक्ट कर रहे थे, वो हमने कहाँ से देखा था?
आउटपुट यही एक्सपेक्ट कर रहे थे जो हमें आउटपुट मिली है ना, वी वर एक्सपेक्टिंग एग्जैक्टली द सेम आउटपुट।
ओके, यानी कि जो हमारा ए था उसको वो डी में कन्वर्ट कर रहा है?
नहीं नहीं, जो हमारा 0 1 स्टेट है वो कन्वर्ट हो रही है A0 1 0 प्लस B1 1।
ठीक है, और ये हमें यानी कि एक्सपेक्टेशन कहाँ से मिली थी? ऊपर से हमने कहाँ से देखा था कि हम ये चाह रहे हैं कि ये हमारे
हाँ,
पास
ये हमने देखा था यहां से, क्योंकि अगर आप इस मैट्रिक्स को 0 1 0 स्टेट पे करें इंप्लीमेंट, इस स्टेट पे, सो वी कैन सी दैट क्योंकि 1 यहाँ पे आ रहा है, तो जब ये मैट्रिक्स से मल्टीप्लाई हो रहा वो होगा, तो क्योंकि यहाँ पे A और यहाँ पे B है इस पोजीशन पे, वी विल गेट अ रिजल्ट व्हिच इज 0 0 A 0 0 0 0 0 B व्हिच इज इक्वल टू A0 1 प्लस B1 1।
ठीक है।
Okay, so let me stop recording.